In this video, I'll cover 8.3, Pascal's principle. All right, suppose we have a fluid in equilibrium so that the hydrostatic equation applies. I've drawn this on the board here. We have the pressure at the bottom is P and at the top of the region is P naught. So here's our hydrostatic equation, P equals P naught plus rho F GH. Let's suppose now that we change that pressure at the top of the region. Suppose we change P naught by some amount delta P. This might mean adding a force on top of the fluid or another liquid, some small amount of change. Okay, then let's look at what happens to the absolute pressure here. So now, instead of P naught, it would go to P naught plus delta P plus rho GH, which we can pull this delta P outside and see that this is just our old expression for P from the hydrostatic equation. So we find that the pressure at the bottom, P, has only changed by delta P as well. And it doesn't matter how large this pressure change is. Pascal's principle says that if an external pressure is applied to a confined fluid, the pressure at every point changes by that same amount. And so we can look at some examples as to how this applies numerically to different situations with fluid pressure. So let's look at the first example. A cylindrical disc of wood weighing 45 newtons and having a diameter of 30 centimeters floats on a cylinder of oil of density 0.850 grams per centimeter cubed. The cylinder of oil is 75 centimeters deep and has a diameter the same as that of the wood. A, what is the gauge pressure at the top of the oil column? And then B, suppose that someone now puts a weight of 83 newtons on top of the wood. What is delta P, the change in pressure, at the bottom and halfway down the column? Okay, so let's have a look at the whiteboard here. I've drawn out what this looks like. So we've got this column here, oil below to a depth of 75 centimeters. And then a wood mass on top of the oil. First, we just want the gauge pressure here at the top of the oil below the wood. So the pressure there is due to atmospheric pressure from the atmosphere and then the weight of that wood. And so our total pressure would be atmospheric plus Fg over A, the surface area of this top of that oil surface. Okay. So if we get gauge pressure, we want that pressure minus atmospheric. So it's just this extra portion, the weight divided by the area. So the wood weighs 45 newtons, and then we have pi and 0.15 meters squared for the radius squared, since it had a diameter of 30 centimeters. To give us a gauge pressure at the top of the oil of 637 pascals. Now in part B, something's being placed on top of the wood that has a mass of 83 newtons. So there's another weight going on here, and this one has 83 newtons. So we can calculate the change in pressure at the top. We would essentially be adding in another force per unit area here to our pressure term. So that's 83 newtons over the same area as before, giving 1,174 pascals. All right, but it asked, that's at the top, it also asked for halfway down and at the bottom. We don't need to calculate those because this is the point of Pascal's principle. It tells us that if that's the change in pressure at the top, that has to be the change in pressure halfway down, at the bottom, and everywhere throughout that fluid, and it's all oil in this case. So this is our answer for both of those parts, halfway down and at the bottom, as well as at the top. All right. So let's look at another version of Pascal's principle. Pascal's principle is the principle behind many hydraulic systems which use pressurized liquids in order to do work. And so one example of this is the brake system in your car. So what happens in the brake system is that your foot would push down on the pedal, which compresses the master cylinder, and then that would drive it into the fluid, creating a change in pressure in the fluid that increases the pressure all throughout and then eventually leads to that fluid applying a force to the brake pads, which will then compress to the wheel. So that's hydraulic brakes. Another example is this hydraulic lift, and we will do some examples with hydraulic lifts. So the principle behind this hydraulic lift is that we'll use a container that has two cylinders of different surface areas. And if they're at roughly the same height, then the pressure at each point has to be the same due to the horizontal line rule. And so we have pressure in equals pressure out. And really this is gauge pressure since we would have atmospheric pressure on both sides. Okay, so the surface area of this smaller input cylinder here of smaller radius is A in, and then we have F in applied to the cylinder there. And then over here on this open side of the container as well, we have an output pressure as that pressure transfers all the way through the fluid and exerts a force on the other side. And the surface area there is A out. So we get this ratio equal because the gauge pressure is equal there. F in over A in equals F out over A out. So why this is useful is because a small force applied here will get multiplied because of this relationship to produce a much larger output force. And so let's look at how that works numerically with an example. Okay, in a car lift used in a service station, compressed air exerts a force on a small piston of circular cross-section having a radius of 5 centimeters. This pressure is transmitted by an incompressible liquid to a second piston of radius 15 centimeters. A. What force must the compressed air exert on the small piston in order to lift a car weighing 13,300 newtons? And B. What air pressure would produce a force of that magnitude? Alright, so it looks like the setup of our hydraulic lift that I had on the board before. I've drawn it again here. And we can apply this ratio relationship, F in over A in equals F out over A out, and we're solving for the input force to lift this car. So rearranging gives me F out equals A in over A out, so F out here, pi 0.05 meters squared over pi times 0.15 meters squared. It's nice to just plug that in for the area because the pi cancels. You don't have to calculate them separately. And that gives 1,478 newtons, which is really amazing. So only 1,478 newtons is required, and then it can lift a car of 13,300 newtons. All right, so what pressure is required to produce this force? We could look at the air pressure either using the A in and the F in, or F out and A out because we know they have to be equal, and that's the basis of Pascal's principle here. So I use the input here, F in over A in. We have our force that we just found over that area, pi 0.05 meters squared, and that gives 1.88 times 10 to the 5 pascals. Let's look at exactly how this force compares to the input force. So if we take the ratio, F out over F in, I have 13,300 newtons over 1,478 newtons, and I get a ratio of 9. So we're applying this small input force and then receiving an output force that's 9 times the input force. So you might be thinking, is this possible? We're getting something for nothing. In a sense, yes, because it's making a process that may have been impossible before now possible. But what's happening is that we still have to have the work out equal to the work in. And if we write that out, F out D out equals F in D out, since both forces would be parallel to the displacement, we can find the ratio of the distance that the force would be exerted over. And it turns out that's 9 times. D in over D out equals 9 times. If you look at that math here, so I've just found that ratio, which is equal to the force ratio. So what that means is that though the force is 9 times greater, in the output, when we're applying the smaller input force, it has to be applied over 9 times the distance. Still, it's usually possible to apply a small force over a greater distance, and it may not be physically possible to apply that larger force over a smaller distance. So it's a really effective device. Let's look at one more example. A barber raises his customer's chair by applying a force of 150 newtons to a hydraulic piston of area 0.01 meters squared. If the chair is attached to a piston of area 0.1 meters squared, what mass of customer can the chair raise? Assume the chair itself has a mass of 5 kilograms. All right, so this looks like the same setup as the previous example. And we can already see that we have a ratio between the areas of 10. So we're going to get the force multiplied by 10 in this case. But let's do the math. So F out over A out equals F in over A in. Rearranging for the output force, we have the ratio of the areas times F in. So 0.1 over 0.01 meters squared times 150 newtons equals 1,500 newtons. And our question was, what mass can the chair possibly lift? So let's calculate this. So we divide that by G to find the mass, which is 153 kilograms. And that's the total mass it can lift. The chair itself has a mass of 5 kilograms. So we'll just subtract that. And it means it can lift up to a maximum mass of customers or anything on the chair of 148 kilograms. Okay, that's all for that. Let me know if you have any questions.